you should consider subscribing to this channel if this content is interesting to you. I'm trying to get to 400 subscribers by the end of the year, so please consider supporting the channel and hitting that subscribe button. Today we're going to be doing Advent of Code Day 13. Advent of Code is basically a challenge where every day in December up until Christmas, Eric Wastl releases 2 puzzles that are related to programming. So we're going to be doing every one of them and explaining the solutions. The code to every day is going to be in a GitHub repository, which is linked in the description. So if you want to check that out, it's linked there. Also, playlists for all other days are going to be linked in the description as well. So, day 13. Shuttle search. Your ferry can make it safely to a nearby port, but it won't get much further. When you call to book another ship, you discover that no ships embark from that port to your vacation island. You'll need to get from the port to the nearest airport. Fortunately, a shuttle bus service is available to bring you from the seaport to the airport. Each bus has an ID number that also indicates how often the bus leaves for the airport. Bus schedules are defined based on a timestamp that measures the number of minutes since some fixed reference point in the past. At timestamp 0, every bus simultaneously departed from the seaport. After that, each bus travels to the airport, then various other locations, and finally returns to the seaport to repeat its journey forever. The time this loop takes a particular bus is also its ID number. The bus with ID 5 departs from the seaport at timestamp 0, 5, 10, 15, and so on. Okay? If you are there when the bus departs, you can ride that bus to the airport. Your notes, your puzzle input, consist of 2 lines. The first line is your estimate of the earliest timestamp you could depart on a bus. The second line lists the bus IDs that are in service according to the shuttle company. Entries that show X must be out of service, so you decide to ignore them. To save time once you arrive, your goal is to figure out the earliest bus you can take to the airport. There will be exactly one such bus. For example, suppose you have the following notes. It gives an example. Here, the earliest timestamp you could depart is 9:39, and the bus IDs in service are 7, 13, 59, 31, and 19. Near timestamp 9:39, these bus IDs depart at the times marked D. So they have this big table explaining when each bus departs. The earliest bus you could take is bus ID 59. It doesn't depart until timestamp 9:44, so you would need to wait 5 minutes before it departs. Multiplying the bus ID by the number of minutes you need to wait gives 295. What is the ID of the earliest bus you can take to the airport multiplied by the number of minutes you'll need to wait for that bus? Okay, so this problem is basically asking, we have a timestamp that we can leave at, and then every bus leaves at some multiple of a number. We need to find the earliest multiple that... Oh wow, wait, this actually isn't a lot. Okay, we need to find the earliest multiple that works. Okay, so let's just code this and then explain the problem. Okay, so we have arrived at our answer, which is this monstrosity of a number here, and it doesn't look quite right. It's not the right number. Okay, so I guess we'll go back to the debugging. Okay, so it looks like I just split by the wrong character. I split by spaces instead of commas. So we're gonna try again. What? Oh, come on. I have 31 seconds left to wait. Well, we'll have to wait then. Okay, so it's probably been enough time. This is our answer. I forgot to multiply it by the amount of time we have to wait as well. What? How is that too high? How is that too high? Come on. Oh, okay. I see. Wait. ID? Oh, we need to multiply by ID. Okay, well, let's fix that. Okay, so we got our answer to be 3215. So hopefully that's right. Okay, that's the right answer. So that took me a while. What's the wrong answer? So let's just explain. As I said previously, the idea here is just to find the earliest multiple of a given bus ID, and that's the earliest we can leave on that bus. So let's just take this example where our earliest timestamp is 9:39, and we're going to consider each bus individually. So for example, for bus 7, we want to find the smallest multiple of 7 that's larger than 939. And to do that, we can just do some basic multiplication. So we can do 939 divided by 7, take the floor of that, multiply by 7. That gives us this timestamp over here, 938. And then we just add another 7 to get to our answer. Alternatively, what I did was actually take 939 divided by 7, take the ceiling of that, so take the largest number that's greater than it. So 939, let's actually do that. So 939 over 7, that's 134.14. So in our case, we'd want to do 135. So we take 939 divided by 7, take the ceiling. So the smallest integer that's greater than the division, because the divided number might not be an integer. So we take the smallest multiple of 7 that's greater than 939 by doing that, 135 times 7, and we get 945. So 945 is the earliest we could take bus 7. For bus 13, we do a similar thing. We do 939 divided by 13, and that gives us some non-round number, and then we round up, which gives us 949. And then for 59, we do the same thing. We get 944, and repeat for all the other buses, and we just choose whichever one is the earliest. So that's pretty simple. I guess I could go through the code and explain which part is analogous to what. We're going to import math just so we can round numbers up. This is just reading in the input, pretty simple. Here we take in the earliest timestamp that we can leave, which is on the first line. Then for all the other buses, we want to make sure that we only add integers, we don't add x's. So we do that. We make sure that every string inside the second list is an integer. And if it is an integer, then we add it to our list of buses. And then for every bus in our list, this is just computing when that bus, when is the earliest time we could take that bus. So that's this line. And if the earliest time that we can take that bus is better than our current best, then we need to update our current best. We also need to keep track of which bus we want to take. And then at the end, we just multiply the ID of the bus that we want to take by the amount of time that we have to wait. So the earliest time we could take that bus subtracted by our earliest timestamp. And that's basically it for part 1. Part 2, the shuttle company is running a contest. 1 gold coin for anyone that can find the earliest timestamp such that the first bus ID departs at that time and each subsequent listed bus ID departs at that subsequent minute. The first line in your input is no longer relevant. For example, suppose you have the same list of bus IDs as above. And X in the schedule means that there are no constraints on what bus IDs must depart at that time. Okay. I needed to think about this for a little bit. Okay, anyway, let's just continue. 713, XX, 59, X, 3119. X in the schedule means that there are no constraints on what bus IDs must depart at that time. This means that you are looking for the earliest timestamp called T, such that bus ID 7 departs at timestamp T. Bus ID 13 departs 1 minute after timestamp T. There are no requirements or restrictions on departures at 2 or 3 minutes after timestamp T. Bus ID departs 4 minutes after timestamp T, and so on. Okay. The only bus departures that matter are the listed bus IDs at their specific offsets from T. Okay, those bus IDs can depart at other times, and other bus IDs can depart at those times. Okay, for example, in the list above, because bus ID 19 must depart 7 minutes after the timestamp at which bus ID 7 departs, bus ID 7 will also be departing with bus ID 19 at 7. Okay, so we only care about what's listed, and extra stuff can happen as well. In this example, the earliest timestamp at which this occurs is 1068781. Okay, and then we see that this happens. In the above example, bus ID 7 departs at timestamp 1068788, 7 minutes after T. This is fine. The only requirements on that minute is that bus ID 19 departs then, and it does. Okay, here's some other examples. Okay, interesting. Oh. Okay. So what is the earliest timestamp such that all the listed bus IDs depart at offsets matching their positions in the list? Okay, cool. When they say minutes here, I'm assuming that they mean timestamps, right? No? Okay, no. No, not necessarily. bus, actually, yes, I think so. I think so, because I think timestamps map to minutes, which is something I think they could have made more clear, because they didn't specify, because timestamps could mean hours, you know. So I think it's minutes. I think one timestamp means 1 minute has passed. Okay, let's just solve the problem. Okay, we have arrived at our actual answer, which is this monstrosity. Still pretty big, a little bit different though, so it's the right answer. Okay, this problem is going to be a lot more difficult to explain and is going to require considerably more explanation. So yeah, I'm suspecting that a lot of people are going to want to watch this video to like understand why this works. So first, I'm going to have to get my drawing tablet. Okay, so I've copy and pasted this into my OneNote page just so we can explain this a little bit better. So first thing to notice, I think, is that I'm just going to explain the theory, and then I'm going to go into the code. So first, the theory. We're trying to find a time t such that it's divisible by 7. So we're just doing this example. And so we're going to say that 7 divides t. Also, 13, when we divide t, okay, so sorry, our timestamp t is going to be 1 before a multiple of 13. So 13 is going to be, when divided by t, is going to have a remainder of 12. And the reason for this is because we can see that there's going to be another timestamp over here, where bus 13 departs. And there's going to be a space of 12 between 13 and our desired timestamp t. So this means that when we divide our timestamp by 13, there's going to be a remainder of 12. So for bus 59, we can say that our timestamp occurs 1, 2, 3, 4. So 4 before a multiple of 59 is our timestamp. So 59 has a remainder of 59 minus 4, that's 55, when divided by t. And similarly, we can say for 31, it's going to be remainder of 31 minus 7, which is equal to 24 when divided by t, and so on. So actually the first mistake I made was I said that 13 has a remainder of 1 divided by t, and it's because I was looking kind of in the wrong direction. So we actually need to kind of reverse it around because remainders work in that way. So just think about it a little bit. 13 actually has a remainder of 12 when divided by t. So we're going to use a little bit of mathematical notation. If you're familiar with this, then it should be pretty easy to understand. But if you're not, it should also be pretty easy to understand. So this is part of a branch of math called number theory, and it deals with, basically, a lot of it deals with how numbers, like what remainders are when numbers are divided by each other. That's called modular arithmetic. That's part of number theory. But mostly number theory just deals with integers. So our notation is we can say t is equivalent to 0 modulo 7. And this basically means that when we divide t by 7, we get a remainder of 0. So that's what this notation means. Mathematicians use it a lot in number theory. So this isn't that difficult to understand. It's just a little bit of symbolism. It doesn't actually mean anything otherwise. We also know that t leaves a remainder of 12 when divided by 13. Oh, sorry, and I should switch this around. There should be t, this should be 13, this should be 59, this should be t. My apologies. That should be flipped around. I'm sorry if you're confused. Yeah. Okay, sorry. So next we also have t is equivalent to 55. T leaves a remainder of 55 when divided by 59, and so on. Now, the important thing is not actually this notation. The important thing to know is that there's actually a theorem called the Chinese remainder theorem, which can actually solve this system of inequalities for us. Not inequalities, this system of equivalences, remainder equivalences for us. Each of these are called equivalences. It's basically like an equation in algebra, except it's for remainders. So yeah, it's called Chinese remainder theorem. And this actually goes back a ways to somewhere in China. Someone invented this, probably. It basically just solves this system of equivalences for you. And I actually saw this on the subreddit. There was a meme about this, about Google Trends, how Chinese remainder theorem was being searched up more often. But that's the idea here. We set up a system of equivalences, basically saying our desired timestamp t has to be equivalent to some remainder modulo the bus ID. And yeah, that's basically what we do in our implementation. And I didn't actually want to implement the Chinese remainder theorem because actually implementing it in practice is pretty difficult. And also, the Chinese remainder theorem doesn't actually give you a solution to these. It just tells you that it exists if all these numbers don't share any common factors. So they're not even, they're not all divisible by 3, etc. You just need to make sure that they don't share any common factors, and then it guarantees a solution for you. It doesn't actually tell you how to find them, but there is a way to find them. And for that, we use a library function called CRT, Chinese remainder theorem library. Libraries are so helpful. You don't actually need to learn anything about theorems. You can just use them. So we just import Chinese remainder theorem, and then we call it on our input, and then we print the answer. And I suppose what I should contribute to this is I should actually explain how to parse the input. So why don't we do that? Okay, so basically we just need to keep an index of where we're in this list right now. So we're going to loop through this list. 19 has index 0, so we know that our timestamp is going to be 19. It's 0 modulo 19. And I suppose I should print this out. So modulos remainders. And these lists are basically just what we have here. This is going to be modulos, and this is going to be remainders. And this is all we need to pass to the library function to get it to work. So I'm just going to explain how we get this from the input. And we can see if we print it out, then we get this list over here. We say it has to be 0 mod 19, 32 mod 41, 724 mod 743, and so on. And how we get this, so we keep an index as we loop through the timestamps. And it starts at 0. And then we go 1, 2, 3, 4, 5, 6, 7, 8, 9. And then at index 10, we hit bus 41. So this means that t, 10 after t, is going to be a multiple of 41. In other words, t is equivalent to negative 10 mod 41 because we're stepping back 10 steps to get to t from a multiple of 41. So t is equivalent to negative 10 mod 41. And basically, once we hit a number, so in our example, I is 10, bus timestamps I is going to be 41. We have to verify that it's actually an integer and it's just not an x. So bus timestamps I is going to be 41. So modulos, we just add 41 to our list. And then remainders, we add negative 10 modulo 41. And yeah, you should be familiar with modulos if you do like this programming thing a lot, because it's a percentage operator in most languages, I would think. So it's negative 10 mod 41, which actually goes to 31. Because like if something is 10 before a multiple of 41, it's also 31 after a multiple of 41 if you just go backwards. So this is going to add 32. My apologies. This is actually 0, 1, 2, 3. Okay, this is actually 9 then, I think. Probably, I think. Okay, so when I is 9, we hit 41. And then we add negative 9 to our list, but negative 9 is also the same as 32. Because, as I said before, something is 32 after a multiple of 41, if it's also 9 before a multiple of 41. So we just do this for every single input. We just keep our index, and then our index tells us how many, what our remainder is for our current timestamp modulo this number. And yeah, so this shouldn't be too difficult to parse. The one thing to know is that you can use the Chinese remainder theorem on it, and there's a library for that. I actually had to search this up, but yeah, hopefully that made sense. Hopefully you understand why it has to be negative instead of just positive. And yeah, I think that today's puzzle was a little bit more complicated than usual, but I think that was pretty fun. So yeah, I think the two main takeaways from this is that don't be afraid to use some simple math or some complex math, I guess, and don't be afraid to use libraries. Yeah, today was pretty difficult. It would have pretty much been impossible to bash this because this is such a large number that it's going to take too long to run. So yeah. Okay, hopefully that made sense. That was day 13 of Advent of Code. All the code is going to be in the code repository in which is linked below. And I guess I could just push that right now. Okay, so now it's done pushing. You can find a link to the repository in the description, as I said before. And playlists to all past and future videos are also going to be in the description. Yeah, that's basically it. Hopefully that made sense. As always, please leave some feedback for me. I always want to improve these videos. Even if it's just like this part could have been a little bit more clear. That's really helpful. As well, you can DM me on Discord if you don't want to like comment. But like, I would really appreciate not spamming. But it's okay. DM me. That's fine for general questions and whatnot, or if you want me to answer specific questions. That's basically it for day 13. If you like this content, please consider subscribing. We're trying to get to 400. I'm trying to get to 400 by the end of the year. And yeah, that's basically it. So thanks for watching. That was day 13. I'll see you tomorrow in day 14 of Advent of Code. Goodbye.